Hi, it's time for another math easy solution. Turn to discuss further into the applied project. How fast does a tank drain? And this is the one I went over question 1 in my last video, and now we're gonna go over question 2. Yeah, and basically, just make sure to watch my earlier video to get a recap on this this applied project. I'm not gonna go over this recap much here, and then I did question 1 in my last video. And now let's just look at question 2. So again, if you haven't seen this question 1 video, make sure to watch that so that you get a better idea of this question 2. And question 2 here states, because of the rotation and viscosity of the liquid when you're draining from a tank, the theoretical model given by Torricelli's law isn't quite accurate. And again, the Torricelli's law is over here. So if you have a tank like this, and then you have a bunch of water and there's a hole underneath with an area A, and then the rate that the volume is draining or it's changing or decreasing of the liquid inside is equal to negative A, that area of this hole, times by square root 2 times gravity G times height of this water or fluid. And then that's all square root inside there. But it's again, the fluid, it's going to be spinning as it goes down, so and it might have a viscosity. Well, all liquids do, so that there's going to be some resistance. So the theoretical model given by Torricelli's law, it's not accurate, quite accurate, because there could be viscosity or resistance in it, so it's not gonna go down as fast as it should, assuming there was no rotation or viscosity, etc. in a liquid. But instead, the model here, dH over dt equals to k times square root h, and then basically where k is just a constant. And the idea behind this model, this is used more often than the theoretical model, and this constant k depends on the physical properties of the liquid, and it's used more often because, well, this k is just determined from data concerning the draining of the tank. So you're actually using physical data or experimental data as opposed to just using this theory of the area times it by this gravity. So basically the idea is to take this area, the square root 2g, and combine them all into a constant. So basically square root 2g and then put this into a constant k, so that we're not actually dealing with these theoretical numbers, but instead just experimental data. So that's what this k comes from. So now question A part A of question 2 states, suppose that a hole is drilled in the side of a cylindrical bottle and the height h of the water above the hole decreases from 10 centimeters to 3 centimeters in 68 seconds. And then it says, use the above equation to find an expression for h of t, and then evaluate h of t, or the height, after 10 seconds, 20, 30, 40, 50, and 60 seconds. So basically this is our experimental data if we're gonna be using this. Yeah, this is experimental data when we're using this differential equation. And so we're starting from 10 centimeters to 3 centimeters. So this means that our h of 0, or our time equals 0, is equal to 10 centimeters. And then after 68 seconds, our h of 68 is equal to 3 centimeters height. So let's just scroll down here. Let's get past this part B. We'll do that afterwards. I'll just put a line like this. I'll do that after this part A. I'll go over that one after. So we have this. Let's write part A. So let's draw it. It's a cylindrical tank. So it's like that. So there's a cylindrical tank with a hole drilled in the side. So let's say it's a hole like this, and then we don't need to know what the area is because it's all combined in that k constant. But we do know is that, let's just scroll up here. So the hole's drilled in the side of a cylindrical bottle, and the height h of the water above the hole decreases from 10 to 3. So let's just draw that. Let's just draw a dashed line representing the water. So this is there, put a little buoy like that inside. So this height here, this above the hole, is going to be, well, let's assume it's just from the center. Yeah, I would assume it's actually from the center, but regardless, it's just a small hole. So we have this is our h of t. And again, initially this is at 10 centimeters. And then basically this is drilled in and it's draining out. Let's draw water draining out here like that. So it's draining out, and we want to find what h of t is equal to, and also h of 10, 20, 30, 40, 50, and 60 seconds. So this is the equation we want to get, and we know, let's put everything down. We know h of 0 equals 10 centimeters, and then h of 68 seconds is equal to 3 centimeters. So, and we also know the differential equation, we're going to be using dh over dt is equal to negative k times, actually, yeah, it's not negative here, it's the just k times square root of h. And then you'll see that k should be negative. Let me just go back up here. Yeah, this whole negative a squared 2g becomes k. Yeah, I forgot the negative. So, and that's written here as well as a k, not the negative. So we have this differential equation. Again, this is a separable one, so we can separate it. We can separate it by writing the square root h, or all the h's on the left side and all the t's on the other side. So we get dh over, this is 1 over square root h, like that. And this equals 2, this is going to be k times dt. And then like before, to evaluate this, we take the integral on both sides. And then on the right side here, this is just a constant k, so this integral is just going to be k times, well, t, and plus another constant. We'll call this c2, because c1 will have a constant on this side. That's just the integration constant. And now this one here, I'll just simplify this, it's easier to find the integral of. This is the same thing as writing h to the power of negative 1 over 2 dh. And then this equals 2, integral of this, well, we add 1 power to it. So that's h of, well, 1 over 2 when you add 1 to this negative 1 or 1/2. So we get this, and then we have to divide obviously by this power, so 1 over 2, like that. And then we have a constant, the integration constant c1. And this 2 can go up on top, so what we end up getting is 2 times, and h power of 1/2, same thing as writing square root of h, plus c1 equals 2, now this. And put that down there, so that's just k times t plus c2. And finally, what we end up, we could simplify this further and combine these c constants together. We get 2 square root of h equals 2k times t plus c, where we just move this over to this other side, where, I'll just circle this, where c is equal to c2 minus c1. Those are just constants. Subtraction of constants still a constant. I'll just write a constant. So that's just another constant of that. And now we could evaluate this further. So we could just simplify this, divide this by 2 everywhere. So we get a square root of h equals to 1/2. Let's write it like this. T plus c. And then take the power of 2 on both sides, we get rid of the square root. So what we end up getting is this is going to be h equals 2. H equals 2 right here. So this 1/2 squared, that's just 1 over 4. And then this is just going to be kt plus c. And then this is all squared. So this is our function of, this is a function of t at the time. The height is a function of t. H of t is equal to this right here, and that's the constant. And now we can begin to solve for this k and c constants, because, well, we have 2 unknowns, k and c, but we also have two known values. That's h of 0 is equal to 10 centimeters. That's our initial value. So when you plug that in, the same thing as writing 10 centimeters is equal to 1 over 4, and then this is k times 0 plus c squared, so that goes to 0. Move this 4 over this side, we get a 40 equals to c squared, and then the square root of this is c is equal to, well, plus or minus square root of 40. again, this is plus or minus because this c could be, when you square it, it's always positive. And I'll get to this further. Basically, to simplify this further, the same thing as writing plus or minus square root of 4 times square root of 10. So the square root of 4 is just 2. So this equals to plus or minus 2 times square root of 10. So if we evaluate it for h of t right away, this is what we get. We get a plus or minus something like this. So that's our c. But the problem here is, yeah, it's plus or minus, so which one do we pick? Well, because of this square, when we square it, and when we square root to get c, it could be plus or minus, but instead of doing that, we could just plug in the value into this equation right away. This is before all this squaring and square rooting, etc. So if we started before, but we know that 2 times square root of h is equal to kt plus c. So this is up to this point here. So now let's just plug in our h of 0 equals to h of 0 equals to 10. So we get 2 times square root of 10 equals 2 k times 0 plus c. So that just goes to 0. So we get c is equal to 2 square root of 10, and that's just positive. So this has to be, well, obviously the positive for our case. Yeah, so that's our c value, and now to find our k value, well, let's just, we know that at h of 68 seconds, this equals to 3 centimeters. So let's just plug that into this equation so we don't need to deal with the plus or minus. So I'll just put this arrow like that. So we get 2 times square root of 3 equals 2k times 68 plus c, which is, well, 2 times square root of 10. So now let's rearrange to solve for k. And when we do that, well, we could move this, let's move the k, actually I'll move this 2 times square root of 10 on this side. So we end up getting as a k, and then divided by 68. So this equals 2, let's put it here. This is going to be 2 square root of 3 minus 2 times square root of 10, then divided by 68. And this is a 2 here, this is all factorable, let's cancel this, and this becomes, well, 68 divided by 2 is 34. So this equals 2 square root of 3 minus square root of 10 over 34. And also my calculus book has it written like this, negative square root of 10 minus square root of 3, and this is because, I'll just put this negative here so it's a whole thing, and that's because the square root of 10 is greater than square root of 3, so that this value is going to be negative. So instead they just put it like this so that you know that it's going to be negative. So square root of 10 minus square root of 3 is positive, and then we have this negative sign out there. So that's what our k value is. Yeah, and now we could combine this all together. So thus what we have is our h of t is equal to, if we write the complete values, is 1 over 4. And then, so that's 1 over 4. Let's just go back up here. So this was 1 over 4 kt plus c and then squared, where k is this. So that's negative. I'll put that on the right side. So what we end up having is this c value, because the k is negative, so we'll put the c in front. So c, which was just 2 times square root of 10, this is 2 square root of 10 minus, now this is the k value, and this is negative 10, negative 3, all divided by 34, and then times it by t, and then all squared. Okay, so now if we, you could simplify this further, so my calculus book does, it expands this. So again, remember the foiling method, I'll just put in brackets like this. Recall, if you have a plus b squared, this just equals 2, or I'll just put a negative because it's a negative. A minus b squared is the same thing as writing a minus b times a minus b. And then when you multiply this by this is just foiling, make sure it's my early video on this. And this by this, and this by this, and add these all up, we get an a squared minus, and this is going to be minus ab, and then again ab minus ab, and then the last one's plus b squared. And then this adds up a squared minus 2ab plus b squared. So just recall that. Let's put this over like that. So recall that. So what we end up getting here is this equals 2. This multiplied by itself, that's our a, that's our b. So we get 1 over 4. And this is going to be 2 times square root 8, square root 10, and then times that together. That's going to be 4 times 10. Because the square root 10s cancel when you square root 10 squared cancels. And then we have on this side we have to have a 2 times, and then we have to have this 210, this 2 square root 10, and then multiplied by this right there, which is square root 10 minus square root 3 over 34, and then there's a t there, so multiplied by t, that's a t over there. And then the last one we add this b squared plus, which is just this here, that's just gonna be this whole thing, square root 10 minus square root 3 over 34. This is gonna be squared, and also the t is gonna be squared here, so the t is squared like that, and then bracket like that. And now we can simplify this even further by just multiplying this 1 over 4 inside. This 2 times 2 is 4. So if we multiply this in, this cancels, this cancels, this all cancels. But then we have a 1 over 4 here. And also this square root 10 multiplies inside to get well, I'll just write this down. So this becomes 10 minus, and to get rid of this big bracket, and then this is going to be square root 10 multiplied inside here. That's just going to be, well, 10 minus, and then square root 10 times square root 3, that's just square root 30. Those just multiplied and divided by 34, and then we have to have a t there, and then this last one is going to be plus 1 over 4 times it by square root 10 times square root 3, and then this is a 34 squared t squared like that, and this is our h of t. So this is the exact values of it, but again we could plug this into the calculator to get, so when you plug this in we get, well, 10 minus, yeah, here I've put in the first part, 10 minus square root 30 all divided by 34, that's 0.133, etc. I'll just round up to 0.133, so 0.133 t. And here I've put in the calculator for the second part, which is 1 over 4 times square root 10 minus square root 3 divided by 34, all squared, and we get this 0.0044, and then etc. But I'll round it up to 0.0044. I mean 30000044. So this is plus 0.00044, and then we have a t squared. So this is our formula rounded up for our height with time. So yeah, that's our answer. Then the other part of part A states, well, find it for when h of t is equal to 10, 20, 30, 40, 50, and 60. And here I put a table here that I got from just made from Excel like this, and you could put a link in the description below for this Excel file as well, so you could see. So here's just that formula: 10 minus, I'll put this here, 10 minus 0.133 times time, and then plus 0.00044 times time squared. So what do we get? And then the first, well, when you have 0, that's just 10, and then 8.7 for 10 seconds. So the height's going down here, and after 60 seconds here goes to 3.6. Then I put the other one, which is 68, so it had to be 3, which just to make sure our formula is correct. Then I also wanted to see how long it would take before it completely drains. That was about 130 seconds like that. Yeah, so let's just go back here. Yeah, so this is the table, and this is right here completely drained. Completely drained, or drained past to the hole, drained to the hole, just make sure. And then here is our this is our data point. So I'll call this data point number 2, and this was the initial data point from the experiment. Data point number 1. And then these are all theoretical ones right here. So from here to here, yeah, so the rest of them are just theoretical ones based on this formula. So now let's look at part B. And part B, it's actually an experimental, basically an experimental test, and it says drill a 4 millimeter hole near the bottom of a cylindrical part of a 2-liter plastic soft drink bottle. Attach a strip of masking tape marked in centimeters from 0 to 10, with 0 corresponding to the top of the hole. With one finger of the hole, fill the water up with the bottle to fill the bottle with water to the 10 centimeter mark. And again, this is just to let you know, this is just trying to experimentally test part A. And then take your finger off the hole and record values H of t for time 10, 20, 30, 40, 50, and 60 seconds. And then it will probably, you'll find it'll probably take 68 seconds for the level to decrease to h over 3. Again, you could test that out yourself. And it says compare the data with the values of h t from part A. So saying compare the experimental data for this time with the modeled one that we did from part A. And then it says how well did the model predict the actual values. And also my calculus book states, well, this part of the project is best done as a classroom demonstration or as a group project with 3 students in each group, a timekeeper to call out seconds, a bottle keeper to estimate the height every 10 seconds, and a record keeper to record the values. And I don't have that kind of time to go over this experiment, but just to help you illustrate what the experiment is about, it's basically you get a 2-liter bottle like this, and then it says drill a 4 millimeter hole near the bottom. That's about here. I think it's about 4 millimeters. Scroll the way back. So that's the 4 millimeter hole, and then so the idea is to drill 4 millimeter hole near the bottom of the cylindrical part of this bottle, and then you would fill it with water up to let's say 10 centimeters. I'll put this in dash lines to be 3D. There is the buoy, say it's water. So that's water. So up to here, we fill it up to 10 centimeters. Let's put this 10 centimeters initially, and this is all in the cylindrical part like that. So that's what we are filling it up to, and then you would basically lift your finger up and then calculate, just record with a stopwatch. How do you look like a, let's put a stopwatch like that, something like that. So you just, and this is a button for example, so you would just record it whenever, and you have a tape measure that's taped on. So you just put a tape measure across or whatnot, or whatever it is, I think tape it on. But anyway, so you would do that as basic experimental data and find h of, so you get h of 10 seconds all the way up to h of 60. So h 10, 20, 40, etc. Yeah, and again, the answers to this part are to be obtained experimentally. I don't have that kind of time. So let's write that down. I've not had the time to do this experiment, but if you do, then please let me know what numbers you get. But according to this article right here, the experimental data matches actually very well with our mathematical model in part A. And I'll get to this paper. This is the articles by Tom Farmer and Fred Grass, and their physical demonstrations in the calculus classroom inside the College Mathematics Journal from 1992. That's a long time ago. That's about 24 years ago. And basically in page 146, 148, you can see this paper right here is the link to it. And basically the quote was, our experience in trying this in 3 different classes was that the experimental data were virtually identical to the Torricelli predictions. That's our part A, making for an impressive and memorable demonstration. Yeah, and here's the paper, so you can download it from that link, and here's another link here. That's just, I think it just redirects to it. But anyways, this is that paper. This is taken from that journal. Scroll up to here. So this is physical demonstrations in the calculus classroom, and then it goes over that Torricelli. The linear one is just not the square root. This is the one we did. It's exactly 10, 8.7, 7.5, 7.44, 3.6, etc. That's exactly here, 10, 8.7, 7.5, 3.6, etc. So that's the one they got here, and that's exactly our model. So, and then the observed data, well, they don't write it down here, but they state it over here. Our experience in trying this in 3 different classrooms was that experimental data were virtually identical to the Torricelli mod predictions, or models, making for impressive and memorable demonstration. So anyways, yeah, if you have time, go over it. It's pretty interesting how you could actually mathematically model such accuracy for the rate that the water drains from this bottle. Anyways, that's all for today. Hope you'll learn from this pretty extensive question 2 of the applied project. And again, make sure to watch my earlier video of question 1 to get a better idea if you haven't already. And also go over question 1, which is pretty interesting. And then in the next video, I'll go over question 3, so stay tuned for that. Anyways, that is all for today. Hope you'll learn from this. A pretty interesting video, and like always, you can download these exact notes and the Excel notes, and I'll put a link to that paper as well in the link below in the description. So yeah, so make sure to check those out. Anyways, that's all for today. Hopefully you learned, and thanks for watching, and stay tuned for another Math Easy solution.